Hi everyone. I'm very happy to see all of you here. Welcome to the Quantum Club. And as usually, we have a warm-up talk which is given by a student, and I will give it today. So I will introduce Christoph Renner, which leads the scanning tunneling microscopy group here in Geneva. And to introduce him, I want to give you a very easy intuition of how works the scanning tunneling microscopy. So of course, if you are a professional in the domain, it will be way too easy, but this is just to give you a bit of intuition. So to do so, in fact, I want to define what is the tunneling. So it's a quantum effect, the tunnel effect. How can we use this to do some scanning? And you will see that the idea of microscopy emerges from these two. So first, what is the tunneling? As I said, it's a quantum effect, but let's step back a bit and see what happened in classical physics. So if I draw some potential, so here we are in classical physics, and I have some potential barrier of 8 V0, you all know that if I have some current that I send in this potential, if its total energy is higher than V0, then the car can pass the potential, okay? And if its total energy is smaller, then the car will be reflected. Okay, nothing special. Now, let's see what happened in the quantum world. For that, I will suppose that I send an electron from the left, and here you have this potential which is a bit more simpler than the one before, to simplify the calculation. And I suppose that I send my electron from the left, and so of course it will go against this potential barrier right here. And I will suppose that the electron has a total energy which is smaller than V0. So if we were in classical physics, of course, the electron will bounce back. But let's see what happened in quantum physics. So we have these three regions, and we know that the wave function of the electron is described by the free Schrödinger equation in the area 1 and 3. And of course, in the area 2, we have to add the potential. And if the energy is smaller than V0, this quantity here will be negative. And we will see what happened in the wave function. So of course, the wave function, if we suppose that the electrons come from far, the wave function is just a plane wave with this k here. And this term here corresponds to the incoming wave function, and this term to the reflection. Okay, so the probabilities are given by the amplitudes here. You have to take the modulus square. And in the region 2, because E minus V is negative, we will have something negative in the square root. So we will have these exponentials with the factor kappa inside. And out of the potential barrier here, I suppose that there is also a wave function which is coming from this side. So I have nothing coming from the right. So the coefficient is 0, this one, I will say. But we suppose that we have something that goes out. And of course, if we were in classical physics, this coefficient will be 0. And now I want to calculate these coefficients. For that, I just ask the continuity of the wave function. So it gives me 4 equations at these 2 points. And I say that A is equal to 1, because I know with probability 1 that the electron comes from the left. So I have 4 equations, 4 variables. So I can just solve it. We'll not do that now. And now we have this result. So we find that F is not 0. So it means that there is a non-zero probability for the electron to pass through the potential barrier. And this is what we call the tunnel effect. And so F is related to the transmission coefficient. So if I take the f, like the modulus square, I have the transmission coefficient, and it's given by this this term here. And the most important thing is the exponential that you see here, because it means that the probability for the electrons to pass through this potential barrier depends on the length of the potential, and we see that it also depends on kappa, and kappa directly depends on V0, so it means that if my potential barrier is very high, it will be also very hard for the electron to pass through the potential barrier. But so this is this coefficient that you have to keep in mind. So it means that there is a non-zero probability for the electron to pass through the potential barrier, and it depends on the length of this potential barrier. Now let's see some physical aspects. So let's suppose I have some atom, very simplified atom, and suppose that I bring a tip very close to that atom. So in reality, of course, the tip is not as sharp as this, but it's, the thickness is comparable to one atom. Okay, so I bring this tip at some distance d to the atom, and let's suppose that I apply a bias between the atom and the tip. Because there is vacuum between the two, I will find some potential barrier, and it has more or less this shape. And I can do exactly the same calculation as before, just what I did in the previous slide. And what will happen? Okay, so this is the tip region, this is the atom region. And if I do the same calculation as before, I will find that there is a non-zero probability for the electrons to pass through this potential barrier. If I have some electrons that pass through the potential barrier, it means that I have some current. And so we call this current the tunnel current. And it exponentially depends on the distance between the tip and the atom. So this is really the main thing that we have to remember. And now let's see what I can do with that. So now I will spend a bit of time on what is the scanning. Let's suppose that I have a bunch of atoms that are just making like a layer of atoms. And I do the same thing as before. I bring a tip very close to the surface. And I apply a potential. I apply a bias between the tip and the layer. And now I have two ways to scan my surface. The first possibility, it's called the constant height mode. So what I do, I just tell to the tip to just fixed its position and just move along the surface. And if I do that, because the tunnel current depends on the distance, I will measure a modulation in the current, and this is exactly what you can see here. So the height doesn't move, but the current changes. And you can see that it's just the line shape of the surface here. Another mode is the constant current, so it's almost exactly the same thing. You bring the tip very close to the surface, but now you say to the machine, when you have some current, please fix the current, and again, because the current is related to the distance, then the machine will have to compensate the height of the tip to keep the same current. And so this will give this graph. So again, it follows, you see the line shape of the surface, but now in the height graph. And now the current is fixed. By the way, this mode is way more safer, because if you have some defect or something which is very high somewhere, then the tip will just follow it instead of crashing in it. And it takes some time to make a tip, so it's better. Okay. And now we can do a bit of algebra. So if you take scanning and you add tunneling, then you find microscopy. And here you can see a quick recap. So it's a video made by Julia Bobrov about this scanning tunneling microscopy. So this is basically the same thing I explained, but better and in 3D. So as you can see, you just receive the current, the tunnel current, and you mark it on a screen, and you can reconstruct the surface of the sample you study. And so now you may say, okay, we have seen a lot of drawings, but what do we really see? And so I can show you this type of images that I had the pleasure to take with Ishita when I worked I did an internship in the group of Christoph this summer. So here you can see a moire. So what is a moire? If you take two lattices that have how we say that, some periodic two periodic lattices. If you just switch one with respect to the other, sorry, not switch, twist one with respect to the other, you will find a superstructure like this, and this is what we call a moire. And so this picture is what we can see with a moire between gold and VSE2. And these two pictures here are just Fourier transforms, so we just treat this image to highlight the structure of the VSE2, or here the superstructure, so you really see the shape of the moire. So this is the type of images that you can make, but you have to keep in mind that this is not an image made by photons. This is just reconstructed using the tunnel effect. And you can also ask, can we measure other things using STM? And I will not answer this question, but Christoph will answer it. Thank you very much.
Thank you all for joining. And what I want to do today is give you really an overview of some of the possibilities that STM, scanning tunneling microscopy, can do. Go beyond a bit what Eliot explained. He focused mostly on imaging, but I will show you that there can be much more than imaging. And the way I constructed this talk is, first I give a short introduction, which I can go fast over certain points. They will be a recap of what Eliot just said, and then I have way more material than I can talk about in the 45 minutes or so, but it's you who will organize the program. Okay, you will see in a moment how that, I hope, will work. So, you know, for all technologies and everything around us, at some point we need tools to observe and characterize materials, right? And at all scales, towards the outer space, towards the inside of materials. And this has probably become even more stringent with the possibilities we have today to combine some of these layered materials into artificial stacks. So this is a cartoon, but really in the labs, we are now assembling materials in a completely artificial way, and you want to know the properties of each layer, you want to know the properties of the assembly under different conditions. And for this, what you need is a microscope of some kind, okay? And the scanning tunneling microscope is one of these techniques that initially the idea was to do simple spectroscopy. So that's something Eliot did not mention, but of course if you have a tunneling current as a function of bias, it's a way to do the spectroscopy, and that's what the instrument was first intended for, and it became famous through imaging. And so now I will show you a bit about all these combinations. So I had in mind to ask you if you know what a scanning tunneling microscope is. So who had heard or seen before Eliot's talk, and who knows a bit what an STM is? So a few, but far from everyone. Yes?
Please also share the screen for the...
Excuse me?
Could you also share the screen for...
Oh, this is not shared?
It's not shared.
Oh, I'm sorry. That's what I was checking, but I thought it was shared. Zoom. Where's my Zoom window?
It's on the screen. Yeah, so I guess it's
Oh,
just-
thank you. That's why. Share. Is it working now? Okay, so some of you have heard about STM before, not all, which is good. So Eliot just mentioned this principle, the basic principle, which is tunneling, so I will not go back into the details, but clearly that's actually a nice older introductory book where you can find some of these principles, but the idea is, again, if you have a particle at an energy lower than a barrier, which could be the surface barrier of some material, there's no way for this electron to escape, and you have to provide energy to go above. And the tunneling principle that he explained is when you have this possibility for the wave function to decay into the barrier, and if you bring now a second surface sufficiently nearby, so this distance d has to be extremely small, then there is a finite probability for these electrons or particles to escape from inside the material. And here we talk about electrons, and they will tunnel between one material and the other with this probability, this exponential dependence on the distance between the two. That's the key element that makes the scanning tunnel microscope possible. It's also the key element that makes it very challenging experimentally to achieve. And just to give you some numbers, typical distances between tip and sample are a few angstroms, so a few tenths of a nanometer. And then if you change this distance by 1 angstrom, then you get a change in the tunneling current of an order of magnitude. And that's really what is at the heart of this experiment. Now, tunneling itself was demonstrated first by Geber and Fischer in the 60s. And it's interesting to see their Nobel talk. So this was awarded the Nobel Prize at the time. And what they did is measure the current between aluminum and lead through an oxide barrier, which is the insulator. And that's what they measured. And this was not only important to demonstrate that tunneling actually works, but here they measured the superconducting density of states. So this would be the superconducting gap in this material. But what's interesting to see is that they said neither Fischer nor I had much background in experimental physics, so they went on tackling a really challenging problem, not having much expertise in experimental physics. And this is why they decided early on in the game not to attempt to use air or vacuum between the two metals. Because if you look at the theory, then the easiest way to do it would be to take two materials, bring them close together with vacuum, and then you measure the current between the two. And they did not choose this because between the two metals because of problems with vibrations. And you should imagine now if you get an order of magnitude change in your tunneling current for 1 angstrom change in distance, which is typically, I was always trying to find order of magnitude, but that's typically 1 over 25,000 of a human hair diameter typically. And variations are yet another hundredth of that if you want to really have a stable junction. And then after all, we both had training in mechanical engineering. So you see, they really thought this is an impossible problem to tackle. So those who decided they would take on the challenge are these 4 people here. I didn't find a picture of Eddie Weibel. But so they set out to construct a scanning tunnel microscope where they would really use vacuum. And also what they would use is not 2 planar electrodes, as in the Geber-Fischer experiment, but they would use a tip instead. And the motivation for them, they were tackling issues of impurities or inhomogeneities in oxides, and they wanted to measure the local density of states to see if they could understand the properties of their materials. And so they decided to take a tip. And if you now consider the sizes, and if these atoms were golf balls, I have one here, then the tip you use would be the size of the Matterhorn. So imagine scanning a carpet of golf balls with the Matterhorn. And to keep it stable at the distance, which is a fraction of this golf ball. That's what STM is doing. Okay? The instrument they built looked something like this, where you have to see on this picture, the sample is somewhere here, and you have the tip mounted on a tripod, and I will come back to how you actually achieve these motions to scan and to approach tip and sample this close. What is interesting here is that because of these vibration issues, this system is mounted on superconducting magnetic levitation. So to absorb and to decouple the instrument from the surrounding, they decided to put this on superconducting levitation. And that's how they decoupled the end part. Of course, there's much more isolation around, but the very final decoupling was done by this levitating system. Now this granted them the Nobel Prize, and what really made the difference is not really measuring the exponential dependence of the tunneling current over distance, because if you have a solid state junction, you can measure this, but you have to make a new sample for each barrier thickness. Here, you simply move the tip, and they could show there is indeed an exponential dependence. But what's really the striking result is this here. This is an image of a silicon 111 surface. And they could solve, at that time, a big issue about the reconstruction of this surface that nobody could solve with diffraction techniques. And so they did this scanning, as Eliot was showing, and they could show this famous, by now, 7x7 reconstruction. And here also to show you how fast technology goes. The data were lines, like Eliot showed. They plotted these lines on cardboard, cut the cardboard out, and glued these things together. That's why you see this width. And this you can see somewhere in a technology museum. Today we have computers and 3D vision and all that. That was really still quite old-fashioned technique, but it was a huge success. And here just a short movie to visualize exactly what is done. So you have a sample surface. You have your tip that you bring really close, and once you are close enough, so as I said, this is typically 5 angstroms, you apply a bias between these two and you measure the current, and then you scan. Then you scan your tip along the surface, and this is now the constant current mode that Eliot was explaining. And you see now if you have these higher lying atoms, if you do it constant height, the tip would just crash into it and you would destroy everything. And then you get these sort of line scans, and that's what they did on the silicon 7x7. And then they cut out these lines to make up a 3D picture of that. And today, what is also quite amazing is that there is a whole lot of materials that you can image with this technique. I'll show you a few examples here. So this is again a modern silicon 7x7 picture. This would be niobium diselenide with different charge density wave. This is a high temperature superconductor. These are some artificial one-dimensional structures we can assemble on surfaces. In this case, it's on silicon, but the 001 surface and some bismuth atoms that tend to self-organize forming these chains. And these are phthalocyanine molecules that you can also image. And what I find quite ironic is that this technique using quantum physics, I mean, it's tunneling, shows the atomic lattice in the way you would sort of play with it as balls. And we all know they're not like that. But here we have a technique using the quantum tunneling effect, and the way it shows you materials are this sort of almost ball and stick model. The sticks are not there, but you will see we are not too far from also seeing the sticks, meaning the bonding or the orbitals that make up these atoms. But STM can do really much, much more than imaging. And one thing I would like to introduce is spectroscopy. So here again, you have the whole circuit with your tip mounted on some piezoelectric drives, the bias voltage between the two, the current measure, and this feedback loop, which if you want to maintain the current constant as a function of position, is always adjusting the Z height to move the tip in order to maintain a constant current. But you can do spectroscopy. In that case, you bring your tip to some location on the sample, and then you completely freeze the feedback loop, meaning the Z piezo is not moving anymore. And you vary the bias voltage and you measure the current, tunneling current as a function of this bias voltage. And then you get what's called an IV curve. So here is energy, that's the bias applied. 0 corresponds more or less to the Fermi level. It's actually the average of the Fermi level between the one of the tip and the one of the sample. And in this case, it's niobium diselenide in the superconducting phase, and what you see here is the superconducting gap. You can take a derivative of this and get a measure of the DIDV curve, which is directly proportional to the density of states. So this you can do either measuring IV and taking the derivative numerically, or you can apply a small AC bias to the voltage here, and then you can directly with a lock-in measure the signal at the same frequency as the oscillation, and you get the first periodicity, I mean the modulation, the current at the same frequency as the bias gives you the DIDV. Then you can go, oh, important here, of course, this is really DIDV when you are at very low temperature, because if not, you get thermal smearing, and small biases. This tunneling barrier that Eliot drew is going to be deformed a lot if you apply very high biases. And you see, this is millivolts, and typically you may be able to go maybe a few hundred millivolts, but then you start to deform the barrier, and you need to correct to really get the density of states out of it. Another thing going yet a step further is spectroscopic imaging. So what we've seen so far is topographic imaging. I showed you spectroscopy, but you can do spectroscopic imaging, and the way this is done, again, you measure this time, again, IV or DIDV curve. Here I show an example measuring the DIDV curve directly, which again is proportional to the density of states of the sample. This is always assuming that the tip is just a normal metal and doesn't have much features in the density of states. And then you scan the tip along the surface in some of the two modes that Eliot has shown, and at each point you take an IV curve or DIDV curve. And then you can map for each position, so this is along a line, the conductance at a given energy, and you take a map of this. So this here would be the conductance map at 65 millielectron volt over a surface 45 by 40 nanometers. And then you can do this for all energies. So you sweep through the energy scale here, and this is what you would see. Oops, not this one, that's too fast. This is annoying, okay. Then you get the local density of states as a function of position and as a function of energy. And you get this at the same time as you get the atomic resolution. So this is conductance at the energy is shown up here. And if I go again, this here is topography you take at the same time. And so you get a full mapping at different energies of the local density of states. And if you notice, if I play it once more, you can see that at certain energies, you will have certain features up here. You see it's pretty boring, but suddenly you have periodic structures. Then they go away again. And here you enter you pass through the superconducting gap, and now at this higher energy you have another structure like these lines, which are actually related to these lines in the topography. So it's a very, very rich data set that we get. Of course, images like this you can take in a few minutes. Really high resolution images like that can take days. Because at each point you need to take a full IV curve, and you have to repeat this over a certain number of points. Okay, so these are sort of the basic principles, and now, as I said, I will not have time to talk about everything. I've prepared sort of 6 topics, and it's up to you to tell me which one you would like to know. So I can tell you more about superconductivity, something about single atom manipulation, what you can do with it, charge density waves, a bit more about instrumentation, and then 2 quite specific techniques. One that gives us momentum resolution, which at the early days was really not something obvious to do with STM. Actually, people early on believed that you could not even do spectroscopy. There were some thoughts that because it's very local, they conjectured there would be some uncertainty principle which would forbid you to get high-resolution spectroscopy. And I never knew which variables they wanted to connect, but some people claimed that this would not be possible. Now we know it's perfectly possible. Or a spin-resolved STM. What do you want to hear about? Atomic manipulation? Okay. So the idea here is to show you that with the STM you can actually pick atoms on a surface, move them where we want. And once you know how to pick atoms, then you can also modify the apex of the tip. I did not mention this but it's probably obvious that this tunneling current is completely determined by the last atom. You know, you could have a tip with a very weird shape, but then it's the last atom, and if it changes, if it's unstable, then the tunneling is unstable. Makes us suffer quite a bit. So I already showed you all these images, and the point now is to go a step further and really take atoms and manipulate them on the surface. And this here was the first demonstration by the IBM team, still not the same guys as those who invented the technique in Zurich. This was IBM Almaden in California. And what they did, they managed to position xenon atoms on a nickel surface to write the IBM. This is really taking atom after atom to position them the way you want. And that's sort of a cartoon picture, but here is a sequence of images taken while they construct this thing, which is a quantum coral. So what they do here is literally a cage of nanometer size. And within this cage, you see these waves appear, which were not there before. And this is quantum confined surface state of this, I believe this was some iron atoms on a copper surface with a surface state. And then you reflect the surface state within this box, and you can show that depending on the shape and size of the box, you get different interference patterns. You get what is called a sort of a phantom object at the other focal point of your ellipse. And so it's all very nice physics, but actually this is completely described by going a bit further with these equations and particles in a box. It's completely nothing new, but it's absolutely amazing that you can see this. And if you play with the defects that you have, for example, if you perturb this shadow part, so there is no real particle, the particle is, you can put a particle here and affect what's happening in this other point. So this sort of indirect influencing feature through the focal point in these ellipses. But you can do amazing physics with this. So here I show you a few examples. So here, for example, they build a chain taking copper atoms on the surface of copper 111. And they can add one copper atom, 2, 3, 4, 5, 6. I mean, they can really put them together. And then they look at the spectroscopy at these points here. And what they see is that as they add atoms, they're actually building up a compound. And so this would be the early stages of building up a band structure. Right? So you have, again, particles in a box with one state, then you have more states appearing, and you can really calculate all these states appearing depending on the size of the structure that you assemble. But this is really atom by atom. I'll probably a few more examples. Yeah, this is interesting. This is a magnetic or a spin chain. These are manganese atoms on a copper nitride surface, which is an insulator. The previous example was on a metal. And here they see very striking effects depending on the odd even number of magnetic ions. And through this, they can learn about the spin dynamics. And what you see here is that the energy for a spin excitation, which is represented by this step, goes down as you increase the size of your system. And this is, again, something that you can calculate. And also, it's very different whether you have an odd or an even number, and this tells you something about the ferromagnetic or antiferromagnetic coupling of the single atoms in the chain. What I should add here, this is going maybe a bit too complicated now. The step you see here, that's something called inelastic tunneling. So when you have a tunneling process, you have your states that can simply go from tip to sample. That gives you one conduction channel. And now if in this system suddenly you have, for example, a spin flip, that can open another channel because you will then, through the spin flip, this is taking up some energy. And then you open another channel for this scattered electron that produce this additional effect, which increases the conductance. So this step here is directly related to a spin flip event in your chain in the tunneling process. This is extremely well documented. So they can really follow this all in great details. Another example I find also quite nice. These are iron atoms on copper 111. And here they apply an external field, not very large. And then you can see these iron atoms, they want to couple antiferromagnetically. And so to have a nice defined chain, this works with an odd number of ions. If you have an even number, I mean, the end, of course, here the end could be up or down, but once you have fixed this, it's defined. If you have an even number, then it's not clear exactly how the system would like to be, either having the two ends up, the two ends have to be in the same state. That comes from constraint with the substrate. And so if it's even, then the system will not know and fluctuate between these two states. So every time you get an even number, you have the images here, and these are spin-polarized images. So the tunneling here is not only sensitive to the state, I mean to the charges in the sample or in the atoms, but also sensitive to the spin orientation of the electrons that do the tunneling. And so the odd number is stable in these configurations, and the even number is fluctuating. And again, that's something quite amazing to be able to see directly in real space. And you can change it by removing an atom, adding one more, and so on. This is a bit for a joke for the gallery, but that also shows what people have tried. This is, in a sense, the highest density memory. So these are 8 octets, and each of this point here is 1 bit that you can flip up or down. And so here they write up to kilobyte memories in something which is the size of, let's see, what is this, 10 times? Yeah, maybe 80 to 100 nanometers by 100 nanometers. So that's extremely dense memory. Of course, it takes ages to write 1 kilobyte, so it's not very useful, but it just shows what can be envisaged with sort of these techniques to make and this is stable. These things, once they are written, they tend not to move, even at room temperature. That's something you can use there. If you go on the web, I don't have it here, the team of IBM Almaden, they even made a movie. I don't know has somebody seen that movie? The Atom Man playing with the ball. So that's made with an STM, moving atoms. So each frame is taken after moving a few atoms. So if you want to look it up, it's quite impressive what they have achieved. Now, I did not say how these atoms are moved around. You could guess a bit in the movie I showed in the beginning. So there's really 2 different ways. One is called lateral manipulation. And in this case, you identify an atom which is sitting on the surface. You approach your tip until you have some interaction, and then you drag the atom along, keeping the tip very close. So either you drag or you push. This depends a bit on the exact materials that you use. There is another technique to move atoms around, which is actually much more interesting, which is vertical manipulation, where you apply some pulse, and then the atom jumps from the sample to the tip and stays on the tip. And then you can go wherever you want and put it back down. This has a very interesting possibility in this configuration, because you see between here and here, or here, you have a different tip termination. So you can start to engineer. That's like changing lenses on a microscope. You can add a filter, but it's a single atom. And so what people do here, so the first example is on a ruthenium surface, and they find a completely different contrast. So this is exactly the same surface, but once they have an oxygen atom on the end at the apex in the right-hand side picture, and in the other case, there is just a tip without this oxygen atom on the apex. And you see here, it's just a change in contrast, but you can imagine, and I will show examples where you can make this contrast useful to learn something about either the material or about the tip. Another famous example, and that's where I said we start to see also the sticks from the ball and stick model. Here what they did is attach a CO molecule to the tip, and by this they can I think this is naphthalocyanin molecule on a 2 monolayer thin sodium chloride surface, which itself is on copper 111. And here they can really start to see internal structures depending on the nature of the tip. So you see here they have a tip with an S wave, so you can really model these things, accurately, not completely, but quite accurately, and they can really see different spatial structures of this molecule, either in the LUMO band or in the HOMO band, and again learn something not just about the structure, but also about the bonding of the atoms making up this molecule. And a final thing, that's something I would like to achieve also in our lab, which is to push this orbital contrast further, but in solid-state materials. And here's an example where this has been, or is claimed to have been achieved on, what is the compound here? So yeah, so this is some cobalt cerium indium compound. If you tunnel at large current, that means, let's say you start with some current and you see some surface structure corresponding to this cobalt surface, and maybe you see a little bit of the lower indium surface. Now you bring your tip much closer, and this you do by increasing your tunneling current. Then you see that these things here start to change the shape. And actually, if you compare the model with this thing, this is most likely a picture of the orbital structure. So now it's not just the electron cloud around an atom seen from far, but going close enough, you can start to see the spatial modulation of your electron cloud, which is, I mean, that's the orbitals. What would be nice now is to do this with a tip, where you could choose the end atom with a certain orbital configuration and do this on and off, not with distance, because I mean, tunneling at 100 nanoamp, that can be pretty destructive. So I don't know how long they keep this resolution, but this is really quite difficult. Okay, so this is what I had prepared about single atom, and please don't hesitate to ask questions if any pop up. That's fine. And we come back to the next topic. Questions about single atom manipulations? No?
Is there like actual applications like for atom manipulation, like construction of
I mean, as I showed, there are more and more experiments where people assemble these single atom chains. You can imagine making a one-dimensional wire. This turned out to be difficult, not because of making the wire, but how you connect the wire to the outer world. That's a different story. I don't know if some people from my team are here. Anybody has an idea of a real application?
Research in fundamental physics.
I don't know, something like memristors also count in data manipulation thing? Like this memristor switchings and so on.
Right, but again, to really come to an actual application, these things are still fluctuating quite a bit. Yes?
How hard / long does it take to actually write something like that?
Excuse me?
How hard or long does it take if we actually want to write?
Oh, I mean, you should. The movie is probably the longest time to make such a short movie. Each of these operations that I showed, you have to come. First, you have to take an image and then really go atom by atom. So it's very slow. It's certainly very slow.
So you're writing the smallest pattern would take you days.
No. So these single atom chains, once you master it, you can make a 10 atom long chain, I would guess, in less than an hour once the system is set up. But you first need to set it up, which can be quite longer. But again, we don't have personal experience moving atoms around, but looking at the time it takes to scan, this is probably what it would take, yes?
Is it possible to automate these systems?
To?
Automate these systems.
Sure. But still, you know, we are talking about atoms, and your tip will drift. Any temperature change will change the place you are, and so there are protocols where you can stay at the same place. And there is actually my first postdoc. He's in a company in the US, Zybex, that do atomic scale lithography. And he's been there for 20 years or so. And they have now some procedures that they can make commercially available, but it's not yet that they can design circuits. I mean, they're getting close, but this has taken a long time. And this is not manipulating single atoms. This is more a kind of lithography, removing single atoms to make devices.
Yeah, I'm trying to imagine which could be the mechanics that allows you the precision of nanometer in positioning and the scanning moving from one atom to another. So again, say a nanometer in 1 hour time and so on. Probably you do this many times, but how does it work from the instrument?
I mean, these are piezoelectrics that move, and then you have a reference image, and you can have somewhere a defect, and there are protocols you could image this defect and then correct for drift, and then you go back to the region not too far away, because piezos have a hysteresis also. And if you come from a different history, you will not end up in the same place. And actually, that's a side remark. So Eliot showed you the scanning, you go forward and backward, and you draw the lines. That doesn't work. The lines will not be the same. So you have to take an image always in the same direction because of the hysteresis loop. But yeah, these are certainly complications. But as I said, this is a commercial company working on atomic scale lithography, and they start to have commercial products. So it can be done.
No, I'm sure it can be done, but I cannot imagine how they will do this.
I mean, these piezos are, apart from the hysteresis, they are pretty reliable. That was actually another surprise, that they have a continuous response down to picometers, definitely. So where do we go next?
Spin resolution.
Spin resolution. So this again goes back to an old experiment on planar tunnel junctions. And here, if you have two ferromagnets, let's say, separated by an insulating layer, you can again do a tunneling experiment. And now the response, if you apply bias and you measure the current, if you flip the polarization to be anti-parallel, the tunneling current will go down. In the extreme case, when you only have spin up and spin down, it could go to zero, because in the tunneling process itself, there is no spin flip. That's the assumption, which is actually verified in quite a number of cases. Now, how is this applied to the STM? Well, now imagine that you have a tip with some ferromagnetic end, meaning a specific spin orientation in the end. And so depending on the relative orientation of the spins in tip and sample, if they are parallel, you get a larger tunneling current than if they are anti-parallel. Okay? And so this is exploited. First example was on a chromium 001 surface, which has anti-parallel, so ferromagnetic surfaces, but where the orientation changes from terrace to terrace. And so if now you image such a surface with a normal tungsten tip, well, then you will see that each step here is the same size. If you go along, oops, I'm spoiling. If you go along this line here, each step will be the same. Now, if you take a spin sensitive, so a ferromagnetic tip, then if the polarization in the tip is parallel to the polarization in the sample, then you get a large tunneling current. And if it's anti-parallel, you get a smaller tunneling current. And this will give you steps which alternate between large, small, and large steps. That was the first demonstration of spin sensitivity in an STM. And here it's large terraces, so there is absolutely no atomic resolution. But you can actually push this to be atomically resolved, and this is a manganese monolayer on tungsten 110 with a tungsten tip, or with a tip which is terminated by iron. And you see this is a completely different contrast. And the difference is precisely the antiferromagnetic orientation of the spins in this tungsten in this manganese monolayer. The thing that people learned is that initially you were using full ferromagnetic tips, because then you guarantee that at the end you have an atom with the proper orientation. The problem with these tips, they have quite a big stray field. So, I mean, it's a magnet that you bring close to your surface, and that can perturb the experiment. Later on, they show that you can also use antiferromagnetic tips, so their overall magnetic field is zero, but still you get spin sensitivity very locally. Then instead of using bulk tips, people started to coat tungsten or other tips with some ferromagnetic material, and then depending on thickness, you can get in-plane orientation, which will be sensitive to the in-plane magnetic moments of your sample, or out of plane to look at spin structures that are out of plane oriented. One problem with this, if you only have a homogeneously magnetized surface and a single tip, you will not know if it's magnetic or not, because, I mean, you see in the previous example here, you can see it because there is a difference in contrast. But if you were just sitting on one atom, you could not say which way it goes. And so people have tried to develop techniques to actually be able to extract the magnetic moment, and that they do by taking a soft magnet material, putting a coil around, and then oscillating the current in the coil to induce an oscillating field in the tip. And this way, I mean, this is probably very difficult. It's been attempted many years ago, but this has not become a mainstream way of doing STM. So I guess this remains quite difficult. But so the challenge to have really a technique to extract the spin component independent of topography is still something that remains to be done. What you can also do is just change the apex atom. So if you replace in a non-magnetic tip the apex atom with a magnetic tip, then you can go from something which is not spin resolved to something which is spin resolved. And here, probably if I zoom, you see here you have a periodicity of 1, which is double here. And what happened is that there were some iron clusters on the surface of this iron telluride that were picked up by the tip. And it went from a non-magnetic to a magnetic tip, which is suddenly sensitive to the spin orientation. And is there one more? Yeah, so that's one other example still from the group at IBM Almaden. So these are different atoms, which some of them are magnetic, some not. And what they did here is they pick up one atom, image the same area, put it back, pick up another one. And by mapping all this, they could actually identify that some of them were magnetic, some not, and that they had cobalt, manganese, and iron. And so you can even start to identify locally what is the atom that you have in a certain place. So again, to go into details, these are, again, these kind of inelastic tunneling curves that I told you before, which have a very characteristic signature depending on the atomic species. Of course, you calibrate this before, but every technique we use, I mean, Raman, XPS, this is all calibrated. We know the XPS signal of this material has this shape because at some point we had to calibrate. So you could imagine that the same thing could be done here. Questions on spin polarized? That's all I had prepared for this part. This is still a field that is just expanding. So all these spin waves, skyrmions, many magnetic structures that are interesting at the atomic scale. People are starting to put efforts into them to study them at the atomic scale. And it can be actually quantitative in certain techniques. Question on that. I don't know how long do you want. I certainly didn't plan to do everything because I said there's way too much. So we have done 2 in. Okay.
A general question.
Yes.
Or for example, if you have a look at the statistics of easy web of knowledge, do you know which are the trends? Let's say there are some topics on which there's more research, or not really depends on.
You mean topics or in terms of techniques? I mean, I could show you. This could help me maybe decide to go for this one to end, because there is really a lot of efforts at the moment, because this is a way to actually access the band structure locally. But I think in terms of trends, there is not a sort of a specific single topic that emerges. So here, this momentum resolution is really something fascinating, because when you do STM, you have a tunneling current, meaning you can see structural features, as I showed you. You can see spectroscopic features, even resolve the spin. Here, what we use is another effect, which is interferences between reflected wave functions on some defects. So this is an example of copper, of a copper surface, and you have step edges. There is no atomic resolution, but you see these ripples like waves at the step edge or around defects. And this is the result of interfering scattered electron waves that are scattered off the defect or off the step edge. So here I just show a model of such a step edge. So you have an incoming wave, the electron is scattered, and then you have these interference patterns which give you standing waves. And the modulations you see here are really these standing waves produced by the interferences. I mean, there's many other interferences, but they may be destructive. You don't see them. Some of them are very special in that they can be form these standing waves. And then you can take images, spectroscopic images, as I showed you, take an IV curve and you plot the conductance as a function of position at different energies. And then you can map out for these different energies the period of these ripples, and they change. They change because the wave number of the electrons depend on the energy. I mean, the K is directly depending on the energy, and so if you plot these periodicities as a function of energy, you can actually map out the band. In this case would be the sort of free electron-like band for this surface state. And you can now do this much more sophisticated. So this is an example of images that you take in real space. So this would be around the defect. You have these standing waves, different energies. Then you take the Fourier transform of these structures which give you information in momentum space, which then you can plot these K values as a function of energy. And if you do this, for example, again, as before on a step edge, then you can do this for many different energies. This would just be one cut at specific energy. You take the Fourier transform and you repeat this for many different positions. And you can then map out really the band structure like photo emission, but actually better than photo emission, because photo emission cannot go into the unoccupied density of states, which STM can. And so here you can do it at a step edge, you can do it at some defect. And so if you look at these compounds, you can actually map out or get a feel directly about the Fermi surface shape, for example. So here you have an example with this is gold on silicon, and here is a different compound which has a different Brillouin zone or Fermi surface topology, and you can, in a way, directly map this out using this technique. So this would be one trend and maybe one example I can show, but it's always a bit the same principle, is that you have in a complicated band structure, like for example this graphene with these Dirac cones, you have certain scattering vectors which are allowed. And again, if you take a conductance map and you take the Fourier transform, this will give you certain spots which you can then identify directly with some of these scattering events which are possible. And you can, from this, reconstruct what's happening in the material. And here maybe one example from our own lab where we looked at what's happening when you have spin-orbit coupling in this system. So just normally you can scatter from one of these cones to another cone from K to K minus or to any other cone in the system, but you cannot really scatter strongly within a single cone because of the spin configuration. If you have spin-orbit coupling in the system, then you change the pseudo-spin structure, and I'm sorry about the jargon, but this is something changing in the overall electronic structure, which then allows intra-cone scattering. And that will give you very small Q contributions which are not seen here. And the way we do this, so you have to take large images. This is a conductance map at 30 millivolts. You see these waves. These are the standing waves happening because of the interference pattern of these scattered electrons. You take the Fourier transform, and I will not tell you about all the points, but you can see it's a very rich thing. What's interesting to us, on the outside, these are just the graphene lattice spots, but then you have these sort of circles here, and you have something at zero, which corresponds to the gamma point in the Brillouin zone. And that's what we will analyze. You can draw the Brillouin zone of this density map, and then look at the features. And we know that these parts here at the K prime points, there's 3 different ones, and they give you this kind of maps corresponding to K vectors that you get from scattering from one cone to the next. What's unusual and new here is that we also have a ring around the gamma point. So here you see the ring is not complete. You see just some amplitude here. But of course, to get a complete ring, that means you need to scatter in all directions homogeneously. As you could see before, it's definitely not a homogeneous scattering. I mean, here you have some waves that look like circles, but here it's more straight, and that could come from a step versus a local defect. But from this, we can then reconstruct the Fermi surface. So at the gamma point, at very small q, which is actually very hard to obtain, we see this ring. which is shrinking with decreasing energy. You can take out the size of the ring, and then you can plot here the dispersion, which is directly a measure of the Dirac cone. And so this is really a way to get also actual numbers that you can then physically compare with numbers from transport experiments and so on. You can play this further again if you do single atom manipulations or if you use existing defects. You can select specific defects which would promote certain scattering, and then you can extract certain specific Q vectors corresponding to these scattering events. So from this you can see changes in the band structure, but you can also learn something about the nature of the atomic defect from these wavelets. And again, if you map this out, you can plot the band structure, these different bands, and again, this is the Fermi level, and we can see this in the unoccupied density, which code emission cannot do. And the final example, this I want to show, this is Alessandro's work, who is here in the room. That's a trick we can play. Usually to get these, what we call quasi-particle interference images, you need to take a full conductance map at different biases, which is taking very long. And then you take Fourier transforms at the different energies, and you see here the things that do not change is the atomic lattice. But then you see in the inside there is this ring which is growing. And from this you could extract again band structure elements, but you can be much more effective if you take a single line and you plot then as a function of energy the Fourier transform of the modulations just along this line. And that means you can extract one particular band, one particular orientation in momentum space. This would be gamma m. And again here this is a topological insulator, you see the gap. And you see here a band dispersing, and this you can understand down here. You see if you go up in energy, the position in Q space is at higher Q. So here if I go up in energy, first at low energy I have an amplitude here. At higher energy my Q amplitude is higher up. That's how you map out the bands. And interestingly there is a little shadow here, which you can maybe see. And that we suspect could be the surface state that would be present if this really was a topological insulator. So here the STM really has very powerful means to tell us more about the intrinsic nature of these materials. And I don't know how long you want to stay.
Can you tell us about instrumentation?
Sorry?
Can you tell us about instrumentation?
That one is short. Yeah, I can tell a few things about instrumentation. And so Alessandro will be happy because then I can use my little camera. Where is it? Instrumentation. Okay, instrumentation. So here, just to give you a feel for the evolution of these instruments. Here is again the first IBM instrument. And then initially also when I started doing STM, you could not buy these instruments. So you would build them, and the main difficulty was always to isolate the vibrations. The stability of the tip is much better than the surface of this table is moving just because I'm talking. The fact that you hear me is there is a wave and things are vibrating. And so initially we would build some of these stacks to decouple, but everything was essentially pretty rugged. There was no sophisticated means. Today we have vacuum chambers, in situ manipulators, and full XYZ positioning of the tip and sample, and you end up with quite complicated environment because you want ultra-high vacuum and you want to be able to put very low temperature and possibly magnetic field. This is an example of the head. So this is what comes inside, not of this system, but some other one. This would be the head where you have some additional vibration damping systems in situ. So these are quite sophisticated instruments. Now there was the question that Pepe asked about the positioning. So the first instrument was done with this kind of tripods. So just using piezoelectrics, these are materials which deform under an electric field. And here if you use 3 different ones which just become longer or shorter depending on the bias you apply, if you have 3 of them, you can move in all 3 directions. Nowadays, we mostly tend to use what's called piezo tubes. So these are a smart arrangement of electrodes on a cylinder of piezoelectric material, which allows you to extend or shrink the cylinder. And then, of course, if you apply the bias in a smart way and that you don't apply the same electric field across the whole cylinder, but opposite polarities on opposite sides, I make this side long, this side short, and I bend it. And this gives you the XY movement and Z movement for the height. So that's how we... Yep.
What's the size of this cylinder?
So typically this would be maybe 2 centimeters, and here between half a centimeter up to 1.5. So it's centimeter size. Can be smaller, it can be half a centimeter in total. There is a third way which is not so popular, which is called shear piezoelectrics. So instead of elongating, they would shear under an electric field. And this just depends on the polarization in the material orientation with respect to the applied electric field. But they can also be used, but are not so as popular as these ones. And then you may wonder, so now I need to bring this Matterhorn, half size of this golf ball. It is a massive thing that I have to bring within very, very short distances. So how is this done? This is again piezo motors. Now I can use this trick here if it works. So imagine that we have a tip, and I have my atoms, and now this is my tip here, but the piezoelectric, you know, they can only deform, it's a few, maybe 100 angstroms per volt. But to be able to load this tip safely, I need several millimeters, otherwise I will crash into my surface right away. And so then to move, you can of course use the piezo, but you could also only move a few, maybe fraction of a micron. And so people have developed many motors, and the most popular now is so-called slipstick or inertial motors, where you give, see, if I move slowly, it's static friction for some memories of last year's or first year course. And if I move fast, I go into the dynamic friction and the tip will slide. And this way, I can bring my tip close, or if I invert the fast versus slow motion, I can move it away. And this is how we move. And I once tried to calculate, so it's like the speed would be a TGV, full speed, so 270 kilometers an hour, stopping a few microns from a wall. So you can move this tip at visible speed, but you can stop within a few nanometers. So that's how the approach is done. And initially, of course, the approach was the main trick, and there were systems with just a screw, so you did it by hand with some differential springs. It was very complicated, and you never knew if the experiment would fail because you crashed. Or here people would not move really the tip, but they have a platform which with the 3 feet would rotate. And you see there is a slope. And so by rotating, it would go down or away. So people have really created all kinds of devices. Today, it's mostly this kind of motors or this one, which is a bit a mix of static and dynamic friction. And here one example of a head that we built in our group. This one combines not only the tip approach, but it can do XY scanning and moving of the sample, because you don't want just to come here, but then you also want to select a position over millimeters. And in addition here, you can rotate the tip around its axis, which if you remember the spin and orbital contrast, that's something we hope can give us an additional degree of freedom to control that. And now what exactly is an STM image? So that's where I said you were wrong on one thing, is that you have to scan and plot the image always, oops, doesn't work this way, always in the same direction because of the hysteresis loop. And so what you do is you measure the tip height at all these points along the surface. That gives you a map like that. You can turn this into a grid. Then you replace every pixel by a grayscale. And that's what is the essence of some of these images I showed you. That's how an image is made. That's topography. And then if you have conductance, instead of having Z height here, then you have the value of the conductance or current or whatever you want. And then, of course, all these fancy color things, that's just cosmetics. You can show But this color scale can then be spin in addition to topography, so you can really start to mix information at the single atom scale. And what else did I have here? Yeah, this one. And tips, that's also something quite amazing. So you know all these tips, in the end you have a single atom doing the tunneling. And the reason we get vertical resolution, that's the quantum tunneling law, so this exponential dependence. The lateral resolution comes from the fact that 90% of the current flows in a channel which is about the size of the last atom. That means you can prepare your tips by simply cutting them. It takes it's a special movement you have to do to make tips that work. But in this mess, there will be some atom further away than the others, and you tunnel with that one. These tips are usually a bit less stable, but they work. Or you do electrochemical etching, which is what actually when I did was the one I preferred, but this gives you very nice and clean tips that you can then also still clean in situ to remove any oxide and make sure that your apex is well controlled, mechanically stable. That's very important, because you know if you have some atom jumping around because it's not well connected or some flake, then it does not work. And yeah, that's what I want to say about the instrument itself. But you're most more than welcome to have a look once, I mean, if you're around. So there is, I see Andreas is here, Tejas, Ishita, Anshuman, Alessandro. So if you can just wave your hand. So if you want to see the lab, do I forget something? No, I didn't see it. So they can happily show you once what it looks in reality.
Thank you.
And so we jump, and I will finish here. Let me just get out of this, and here. And thank you very much.
Thank you, Christoph. Do you have any questions? You're welcome to ask it now, or you will be welcome after in the apero.
I have one maybe very childish question. So about the tip, and
Yes.
you're always talking about the very last atom.
Yes.
But is it possible, and if it is possible, what does it do so that it will stick to the material? And you actually
Oh, this happens. I mean, when you have an unstable condition, you can see your scan, but then you really see it in the scan, it's changing.
and then you have
Usually we don't know, we cannot, this is one possibility. This happens, and the thing I showed you with the spin resolution on the iron telluride, that's exactly what happened. And initially it was an annoyance until they realized actually they had reproduced the spin-polarized tip.
and then you have to change the whole tip.
Not necessarily. So again, they will be able to tell you much better. You can usually what we do is these tips are conditioned on gold or silver until you get a spectrum that you like. So these have a surface state, and so you make sure you have some imaging resolution and some spectroscopy. And if a tip goes bad, you can go back on gold, and what, 5 times out of 10 you recover it. So yeah, there is a way to recover. Ciao.
No more questions? I just need you 2 more seconds. We try to do better advertising with Quantum Club, so if you can just scan the QR code to tell us how did you know about Quantum Club? And you are all welcome. So we do now an apero outside where you can ask questions to Christoph. Maybe it will